So what's the big deal? I mean, you know, what's magic about buses? They just seem like bigger logic circuits with, you know, wires measured in many inches or maybe feet. Can't we just live with that? And the answer is no, but, you know, we take a little getting to that conclusion. So the first thing, you know, you say, look, come on, wires are, you know, the abstract notion of a wire is this, you know, equipotential way of electrical node that where basically it has the same voltage everywhere all the time, at the same instant everywhere along the wire. And that's an abstraction which works well sort of locally. It works less well when we start thinking about long wires and fast transitions of voltages on wires and things like that. So, but at least in the abstract, we don't worry about time. One of the advantages of abstracting out, of having this abstract notion of wire is that we say, look, we're not, you know, the time that it takes to transmit information physically from one end of the wire to the other at one point in the technologies was very, very fast compared to the speed of the actual logic gate, so it was essentially negligible. The transition that's happened is no longer negligible, and in fact, it may in fact represent the lion's share of the timing budget now. The logic gates, you know, operate in a couple picoseconds. Transmitting the information over a 1-inch wire takes many times that time. So it's sort of been interesting to watch how the generations of technology have turned on the head what was important. So this abstraction turns out, which was fine in the original computer architectures, turns out to have had to have been replaced by a much thorough understanding of how interconnect actually works. And how, in fact, every time you transmit a signal, there's actually you know, a lot of interesting E&M that happens, electricity and magnetism that happens, and you actually have to understand that in order to have the transmission happen in as shortest time as possible. The notion that, you know, we're dealing in time spans where even passing information over an inch is huge. You know, we don't have enough time in our time budget to allow for a 1-inch transmission at the speed of light. So, and we could say, oh, well, just forget about it. But if we did, our processors wouldn't run at, you know, 2 gigahertz or 3 gigahertz or 4 gigahertz. They'd run at, you know, these sort of, the abstraction didn't give us enough information. This nice abstraction didn't give us enough insight into what was happening for us to engineer things, you know, to take advantage of everything we could in terms of speed. So in the abstract, think about, you know, you can think of, you know, here we're transmitting information. If we're just simply moving information, you know, in time, we're sort of just thinking about storage. And, you know, in the nice abstract way, we could think about communication really as simply moving information from one place to the other. And it would be nice if those two axes were sort of independent. But the point I'm trying to make in today's lecture, and something that will affect the engineering greatly, is in fact we can't move information across space without also considering that it takes time to do so. So that's really, you know, we have all these sort of low-level things where you're saying, oh my goodness, you mean Maxwell's equations really matter? And the answer is, sadly, yes, we've reached an era in which the speeds that we're dealing with, they do matter. You know, the fact that light only travels so far in a nanosecond or a picosecond is now a limiting factor for us. We do know that even though our devices are small, if I put 1 billion of them on a chip, it's going to take, you know, centimeters to do that. Our chips actually take real space, and then, you know, the transmitting information across the chip turns out to be a multi-cycle thing. It doesn't happen in a single clock cycle anymore. And finally, you could say, well, you know, we'll just, you know, what makes things slow anyway, or fast anyway? And the answer is, well, you know, we're charging and discharging these nodes. We're using these voltage-based representations of information. And simply charging and discharging capacitances through these switches takes time. And, you know, the way information gets propagated along wires takes time. So, and you begin to see that now, because some of the interconnect on chips is turning to be optical, which is sort of odd, right? I mean, the idea that there's these tiny microscopic lasers shining, you know, shining at the other end of the chip in order to get information across the chip faster than it could get if you just tried to put it on a piece of copper wire. That's sort of remarkable, but that's what's happening now. Okay, so the real truth about wires. This sounds like the name of, you know, I doubt that it will become a Hollywood hit, but it sounds like, you know, okay, expose. The Republican senators will want to hold a hearing. Okay, you know, can't we just legislate fast wires? And so, you know, the answer sort of is, well, we developed an abstraction where we sort of bundled all the delay, the intrinsic delay of the gate, plus the delay of putting information out and, you know, charging and discharging all that capacitance, you know, into one timing number. And that was a convenient abstraction that made it easy to think about the timing of a circuit. But the truth of the matter is that if I have a heavily loaded signal, here's some select signals, you know, the select signal, which is actually visiting 32 2-to-1 muxes, right? So this is all 32-bit buses. So I have 32 copies of these 2-to-1 muxes, each of which is dealing with 1 bit of this 32-bit mux. And we begin to realize that there's a lot of loading on that select signal. It's suddenly going to 32 different logic gates. And that signal will be a lot slower than if it only went to a single logic gate. So this notion that we actually have to think about the loading, and that a better timing model, you know, conceptually not as clean and as elegant, but would allow us to do a bunch of engineering that we can't do otherwise. A better timing model is to say, look, I'm going to think of the gate as having an intrinsic delay. How fast would it be if it had no loads on it at all? If I just, you know, looked at the output, it didn't go anywhere. And then I'll separately account for how many things I'm hooking to it. So if I go from hooking 16 things to it to hooking 32 things to it, right, I would expect in some ways some component of my timing to now be twice as slow, because there's now twice as much capacitance to charge and discharge. And so somewhere along the line, our timing model should probably take that into account. There are things that will take hundreds of picoseconds, signals that will take hundreds of picoseconds to change, even though the logic gates themselves are operating in tens of picoseconds, right? And you could say, woo, it turns out that if I'm a bit careful about how I, you know, instead of having one signal go everywhere, suppose I made 5 copies of the signal and have them each go to 1/5 the number of places, that'll turn out to make your beta noticeably faster. In fact, you can make almost a factor of 2 difference in the clock speed of your beta by taking into account these issues about loading and carefully distributing signals such that no one signal has to do all the work. Okay, so it's actually an interesting thing to suddenly peek under an abstraction, and is, you know, and I think people are always doing this. I have this great abstraction that's worked well for years, but if I look inside, is there an opportunity to do something better that used not to be possible because the technology has changed? And would that cause me to think a little bit differently about the abstractions I chose, particularly if I'm interested about power or performance? Okay. So one of the big issues is, how do I communicate things, you know, across something the size of a laptop, right? I mean, I was just moaning about communicating across a chip, but your laptop is, you know, 10 inches wide, or your desktop is, you know, is a big box. Getting information around that system requires sort of a rethink from sort of the old days to the new days.